I have a good story. We got to prank call some people last night. That was fun.
Welcome to the 1980s. Okay. Because I never did that growing up. All right, we're good. We got it. We understand what's going on. We had a good review. You don't have to have me run through all of this stuff because you totally just did it yourselves. Yes, we're good? We're happy? Okay, all right. Today, here's what we're going to do. Before we get into finding these solutions by magic, because that's where we're at, we have this magic that we've been trying to use to find these solutions, and we would like to not have to have these magic solutions appear. We would like to do it ourselves. But before we get into that, one additional thing from today, which is initial value problems. So here's our goal for today. Turn, this is magically obtained, general solution into a particular solution using initial conditions and here's the key point, systematically. That's going to be important in this case. We want to do this systematically. It's solving equations for unknowns. So you could totally do this unsystematically, no problem. But we want to do it systematically. So if you have taken linear algebra, you are going to be super familiar with what we've done, what we're doing today, because we did it up the wazoo in linear algebra. So what we are going to do is create an augmented matrix. If you haven't taken linear algebra, you don't know what that means, that's okay. Create an augmented matrix and use elementary row operations. You should be having very pleasant flashbacks to linear algebra if you have taken it, because this was stuff you got really, really good at, I think, I'm pretty sure. All right, so create what's called an augmented matrix and then use elementary row operations. Let me write out what the 3 legal elementary row operations are. Actually, no, people can volunteer. Legal elementary row operations, either in the chat or verbally, people who have taken linear algebra. There are 3 of them. What are they? What are you allowed to do? Virtual hand raise for me, please, or you can put it in the chat. Either way, what do you got? There's like half of you who have taken linear algebra. You all took it with me. Okay, there's one in the chat here. Interchange 2 rows, absolutely. That is the second one. Second one, interchange 2 rows. Jason had a hand up. Jason, interchange.
Add or subtract rows?
Kind of, yes, sort of. So that kind of gets put into number 3. What do we have with number 3?
Multiply a row by a number and then add or subtract?
Yes, yep, multiply a row by a non-zero, we would say scalar or constant. That's supposed to say non-zero, it does not. Let's try non-zero. By a non-zero, I'll say scalar, but constant works as well, and add to another row. Cool. What's my elementary operation number 1 for people who have had linear algebra with me? We didn't use this one very often to get rid of fractions more than anything else. Elementary operation number 1, someone besides Daniel and Jason, because they have kindly volunteered for me already. What do we got? Ladies and gentlemen, you are having me doubt my linear algebra teaching abilities. What do we have? What's elementary operation number 1? Let's see. Okay, now we're back to the, I don't even know what in the chat. Elementary row operation in the chat. You haven't taken linear algebra, Stuart. You're not helpful at this point in time. Bethany.
Was that just multiplied by a non-zero scalar?
Yes, thank you. Multiply a row by a non-zero scalar. Multiply a row by a non-zero scalar. Okay, and our goal in doing these elementary row operations, I should have set this up here, use elementary row operations to get a triangular matrix. I'm teaching this backwards from how I usually do. Usually I do an example first and then I say, oh yeah, this is the stuff that we've done. We're kind of doing it backwards today. Let's talk through the theory first and then we'll do an example. So in essence, what this is a really fancy way of eliminating coefficients and solving a system of equations. That's basically what's going on. We're just going to make it systematic. So let's look at an example and it'll make a little bit more sense here. For example, here's my system of differential equations. So my system of equations is going to be 3x1 minus, x1 prime. x1 prime equals 3x1 minus 2x2. x2 prime is negative x1 plus 3x2 minus 2x3. x3 prime is negative x2 plus 3x3. So this is my system of equations. x1 prime equals 3x1 minus 2x2. x2 prime is negative x1 plus 3x2 minus 2x3. x3 prime is negative x2 plus 3x3. Here's my general solution. Nope, sorry, here's some particular solutions. So here's my solutions obtained by magic. Solutions obtained by magic are going to be, these are vectors. So x1 is equal to 2e to the t, 2e to the t, e to the t. That's my first vector. x2 vector, negative 2 e to the 3t, 0 e to the 3t. And vector x3 is going to be 2e to the 5t, negative 2 e to the 5t, e to the 5t. Grant, question.
Did you get those from the system of equations or did you just
Magic. Those are magic. So when we get into 5.4, we are going to do the magic that will let us obtain those. Right now, still coming by magic. Totally magic how those came. All right. I also have initial conditions. So here are my initial conditions. x1, vector x1 of 0. That's not vector, sorry, that doesn't make sense. Let's try function x1. So x1 without a vector arrow of 0 is equal to 0. x2 of 0 is equal to 0. And x3 of 0 is equal to 4. Those are my initial conditions. x1, not the vector, the solution. x1 of 0 equals 0, x2 of 0 equals 0, x3 of 0 equals 4. So the first thing we have to do, because I don't have x1, x2, x3 in this case, in terms of x1 of t, x2 of t, etc. We got to use the principle of superposition to find our general solution. So putting all of these back together, we can come up with a general solution. We can either write it, and this is where, again, I want you to get comfortable with both ways of writing it. Vector x, so this is going to be 2c1 e to the t minus 2c2 e to the 3t plus 2c3 e to the 5t. I kind of put the constants after the coefficients, right? So we've got c1, c2, c3. Tell me you're okay with where the c1, c2, c3 are falling, right? That part makes sense, that's okay. And then also remember this notation. So this first line here then is the function, not a vector, function x1 of t. That's the notation that we're using in this case. This is a system of equations. It's going to have 3 functions as solutions. So these 3 functions are coming from the first line, the second line, and the third line of our general solution. Okay, so you got to be really careful with when you have vector arrows and when you don't. Next line is going to be 2c1 e to the t. The 0 is just going to be a 0 in the second part, and then minus 2c3 e to the 5t. So we've got a 0 in that second piece. Okay, and that second line, again, remember your notation. This is the function x2 of t. No vector arrow over the top. This is the function x2 of t. Third one, c1 e to the t plus c2 e to the 3t plus c3 e to the 5t. That's my third one. And then for the third time in this problem, this one, last row, is x3 of t. No vector arrow over the top. All good? All good? We did that yesterday. I haven't done anything new yet. This is all from yesterday. We're good? Give me a thumbs up. Yes, good, nodding. Okay. All right, so now what I can do is use my initial conditions. So initial conditions, here's what I'm gonna have. I'm gonna write it out this way, and so for this, I'm going to put, just to remind you, plug in t equals 0, right? Because all of my initial conditions are x1 of 0, x2 of 0, right? So those can go away. All my e's are gonna go away. Here's what I'm getting for my initial conditions. 2c1 minus 2c2 plus 2c3 equals 0. That's from my first initial condition that I had right here. x1 of 0 is equal to 0. So when I plug in 0, all the e's go away, and I got my coefficients out. I'm going to have a 0 on the right-hand side. Do we see where that's coming from? Putting them? Okay. All right, cool. Next one, 2c1 minus 2c3 equals 0. 2c1 minus 2c3 equals 0. All right. And then my third one, c1 plus c2 plus c3 equals 4. Not 0, but 4 this time, because that third one was equal to 4. All right. Everybody good? We're good? So now here's the systematic part, and this is, again, not differential equations. This is linear algebra. We are totally mixing differential equations and linear algebra in this chapter. You could, if you wanted to, use high school math techniques to solve this system of equations for C1, C2, C3. You absolutely could. I don't wanna, because I wanna make it more systematic, but you totally have the tools to solve this at this point in time. They're just not good tools, unless you've taken linear algebra. So we're gonna give you better tools to solve this. I am